Today I'll be talking about high-resolution hydrological models over Europe using CLM and ParFlow, highlighting recent model and application developments. A lot of my talk I'll be actually describing some of Bibi's models. Sorry, I'm not sure why this is... Sorry about this. A lot of this talk will be describing some of Bibi Naz's work. Unfortunately, she couldn't make it to this meeting, but hopefully if there's any questions on her work specifically, if I can't answer, then Stefan Collette can probably jump in. Okay, so the first part of this talk is about assimilation of remote sensing soil moisture data using the CLM PDAF model. This is to improve soil moisture estimates, as soil moisture is a key driver for stream discharge and water exchange at the land surface, and assimilating observational soil moisture data can improve not only simulated soil moisture but other important simulation fields such as discharge. So on the right-hand side we've got the CLM land surface model, which is forced with observed meteorology, and it's a complete space-time coverage including root zone. And then on the left we've got the ESA CCI remote sensing soil moisture data set, which is the upper few centimetres at 25 kilometres at a temporal resolution of daily. And so what we do is we feed that into the data assimilation framework from the model estimates and from the remote sense data estimates, and then we improve the soil moisture and indirectly improve the discharge as well. And how we do that is we use the Terrasis MP PDAF platform, which includes Cosmo, which is an atmospheric model, ParFlow, which is a groundwater watershed model, and also CLM, which is the model we're talking about at the moment. And so we just take a part of that, CLM, and use the coupling interface to PDAF developed by Kurtz et al. And then we leverage the parallel data assimilation framework developed by Nerga et al. And what we do is we can do a simultaneous update of 10 to the 7 states and 10 to the 7 parameters with that framework. So first of all, the CLM model setup without the data assimilation is that we've organised several different key inputs, such as GMTD 2000 elevation dataset for topography, soil characteristics from the FAO global dataset, vegetation LAI from MODIS, and the land surface classification from MODIS. And we organise this at 3 kilometre resolution, and then we force this model with Cosmo reanalysis at 6 kilometres for the simulation period of the 1st of January 2000 to the 31st of December 2006. And there you can see some of the different fields, percent sand, percentage clay from FAO, and the elevation and also the land use index there on the bottom right. So then to actually get the improved states, we use a Kalman filter, an ensemble Kalman filter, where we have 10 ensemble members and we perturb the precipitation and then the soil properties, percentage sand and clay, which we saw in the previous slide. And then to get the updated state vectors from assimilating the observation and the model. The Kalman gain matrix is used, which is like a weight matrix which combines model and observation covariance matrices. So a little bit more about the observational data set. For assimilating the data, we use 100 grid cells, which are randomly selected where daily data are available. There's more data gaps that exist in the winter and because of cloud cover and in the earlier time period. And the data coverage of observation is low in Northern Europe compared to southern areas. And in order to validate the model, we're looking at ultimately improving our runoff as well as soil moisture. So we compare our model to the eRun gridded monthly runoff, which is run at a coarser resolution, 25 kilometres, from Goodmanson et al. So looking at the comparison with the open loop, so open loop actually means no data assimilation, and the CCI remote sense data, you can see that the spatial resolution is different between the two. The temporal resolution is daily compared to hourly for CLM. There's sparser coverage in the remote sense data compared to good coverage with the CLM model. And there's a challenging error structure inherent in the remote sensing data, and the model error for the open loop is difficult to estimate due to various things such as the model parameterization, the input data, etc., etc. So looking at the seasonal soil moisture then, when we compare the remote sense data with the open loop, which is no data assimilation, to the data assimilation, which is on the right-hand side, -DA, we can see that the open loop CLM with no data assimilation has a wet bias. So there's a higher soil water content in all seasons over most part of Europe compared to the data assimilated ones, and also the remote sensing data itself. And the soil water content in the summer and autumn is better reproduced in the CLM DA simulations than when compared to the open loop. And looking at the different prudence regions, which are noted up in the top right-hand corner, you can see that the CLM DA, which is in red, is closer to the observations, which are in their black circles in most of the prudence regions, looking at the daily soil moisture. And quantifying that now, we looked at getting a root mean square error and a mean bias error and comparing the open loop with the data assimilated version. And you can see that there are improvements in terms of RMSE and they're overall, and they're more pronounced in the SC, AL, MD and EA regions. So that's the top and Mediterranean and Eastern Europe. There's a negative bias error in the summer in the data assimilated versions. Okay, and then if we look at the validation of monthly runoff, because that's ultimately what we wanted to improve indirectly by assimilating the soil moisture, you can see from the red compared to the black, there's a definite improvement when we use data assimilation over the prudence regions. And the improvements in terms of RMSE are more pronounced in the SC, AL and EA regions, and in the spring season, particularly because in the spring you get higher rates of precipitation, which then exacerbates the wet bias. And there's a negative bias in the CLMDA for runoff overall. So the summary and outlook, looking at the CLM PDAF model, assimilating monthly ESA CCI data improves the RMSE of soil moisture and runoff outputs. Improvements in terms of RMSE are more pronounced in the SC, AL, MD and EA regions. And number 3, CLM, the data assimilated CLM version underestimated runoff in the summer and autumn seasons, particularly in the mid and south Europe. And this maybe has to do with coverage, data coverage. The next steps would be to, instead of just updating the states, we update the model parameters and we validate the assimilated models using independent data sets. And then we include the groundwater and atmospheric model in our for the Total Terracis MP PDAF platform. Okay, so now looking at the same model, but now we're including groundwater dynamics. We use ParFlow for this, so we've got the same key hydrological model inputs at 3 kilometres, plus this model was set up to a depth of 60 metres with 15 layers, so there's 3.7 times 10 to the 7 grid cells, and this is not a column model, this is a fully 3D dynamic model, unlike CLM. And interconnected European river networks as aquifers have been added to the IMHE subsurface geology in this, the bottom figure, in order to achieve more realistic groundwater flow through the continent. And we use the same meteorological forcing, and at the moment we're running spin up for the period of 1st of January 1997 to the 31st of December 1997. And the spin-up is ongoing and expected to finish or converge by the end of the year. It's quite costly to run ParFlow. 1 year equals 10 days simulation time. Here I've shown the water table depth and the river flow for year 4 in the month of January. And to validate this model, we first made sure that the forcing is okay, so we had a look at cumulative distribution functions of precipitation, which were compared to climate station data. The river flow is evaluated using GRDC data, where drainage area of stations are matched to drainage areas of simulation within 10%. You can see the 2 plots of the observation area versus the simulated area, and the locations of the GRDC data are on the top. And then we look at the water table depth by comparing the water table depth generated by Fan et al. 2013, which is constrained by observations, and you've got the global water table depth in the bottom figure. So because I mentioned that running ParFlow is quite costly, we've done some improvements to ParFlow to try and mitigate those costs temporally and computationally. And so the first thing we did was integrate ParFlow with pForest, which is a very efficient, highly scalable, adaptive mesh refinement library to take care of all the gridding. And this resulted in a significant reduction in setup time and a significant reduction in memory use. And now ParFlow scales to the whole of UQueen, as you can see from this plot below, where you've got the different numbers of grid points ranging from 6.71 million grid points to 10.5 billion grid points, and it's a member of a high Q club now. Another thing we did is to integrate parallel netcdf for I/O with ParFlow. This will tackle the big data challenge by making the output highly portable. netcdf for I/O has nice features such as chunking and compression, and it's scalable as well. As you can see on the figure on the right bottom side, there's a scaling plot, and this plot on the left is showing how each node writes a portion of the data to disk. And also to be ready for exascale, I think we also need to look at what the upcoming hardware and software is going to entail. So we're adapting ParFlow to next generation hardware and software via the use of a miniup. The reason why we're doing that is because ParFlow is quite unwieldy in comparison. This is very lightweight, it's simple to run, and it's flexible, and so many different collaborators can use this on many different platforms. It's, as you can see here, we've set up the permeability as a random log normal distribution, so to emulate the heterogeneity in the models that we run. And on the plot, looking at the architecture comparison, we've got K&L in red, normal CPU in orange, and GPU in dark red triangle. And the K&L and CPUs, obviously the K&L scales quite well, but it takes longer. The serial performance is worse if you compare the same degrees of freedom, so the 64,000 degrees of freedom. The GPUs produce the fastest time, however the scaling is not that great. So probably more needs to be done to explore different heterogeneities and everything else, but this is our initial results. And the other thing we did to ease the burden of development and to streamline development and also aid production runs is we integrated ParFlow into a run control framework to automate all aspects of the modelling chain, from pre-processing, the environment preparation step, compilation, the simulation run step, and the post-process and analysis step. This run control framework leverages Dube, which I think you guys have all heard of, but could be adapted to any workflow engine. And it can also be used for profiling testing and as well as production runs, and it contains the standard profiling tools and workflows that people use on HPC systems. So the summary and outlook for ParFlow is ParFlow models and development. High resolution continental models are computationally and temporally costly to run. However, there are obvious benefits to using a fully 3D physics-based model. For example, there's physical consistency, there's realism, there's no need for a routing scheme, etc., etc. Improvements have been made to ParFlow to reduce the cost of running complex continental models, as we outlined before. However, still more can be done. And we're still at the exploration stage with regards to next generation hardware. We've only used one solver library at this stage, PETC, so we could use different things like sundials. And more testing should be done before implementing what we've learnt into ParFlow. And one of the main science questions that we can answer with ParFlow, having this highly resolved continental scale model, is examining the continental submarine discharge in order to characterise the groundwater flow through the European continent. Okay, thank you very much. Sorry about the technical problems.